Hi, in this tutorial we're just going to go over the Diels-Alder reaction. The Diels-Alder reaction is a 4+2 cycle addition reaction which is thermally allowed according to Woodward-Hoffmann rules. But if that's a bit too advanced at the moment, what I'll do, I'll bring that, another tutorial to explain Woodward-Hoffmann rules and thermally allowed processes in the future. In the meantime, I will try and explain everything that happens and what actually makes this reaction work, why we get certain stereochemistry that we do and certain orientations of the reaction intermediates. So let's begin just by explaining the process. If you see in the beginner's tutorial to Diels-Alder reaction, we have a diene, which is this. It's usually in the cis-oid conformation as opposed to the transoid, which is like that, so it's trans to itself. The transoid, if I just write that out, transoid is thermodynamically more stable than the cis-oid because you'll get some steric hindrance of these protons here, and these are all nice and away from each other. But unfortunately, it needs to be in this orientation to react with the dienophile. So what happens is, this is always in equilibrium with each other, and you've got basically Le Chatelier principle, where this one will get eaten up. Let's say this is like 10% of the whole overall mixture. It'll get eaten up, and then this will transform more into the cis-oid stereochemistry. So you've got the cis-oid and transoid, but it's only the cis-oid that will form the Diels-Alder product, or adduct as it's called. Another important feature which I didn't really touch on in the beginner's tutorial is the reactivity of the dienophile, this here, and I'm just going to put EWG here, and that basically means an electron withdrawing group. And in this tutorial I'll probably use an aldehyde or something like that to just pull the electrons away. And what we're trying to do is we're trying to differentiate these double bonds here, because it's the double bonds, it's the p orbitals that are reacting with these p orbitals, and so they need to be attractive to these electron-rich p orbitals. And we do that by making them electron deficient, by pulling the electron density away from the p orbitals, and we do that with an electron withdrawing group. So we got dienophile here, dienophile, and that reacts with the diene. Okay. So just to go over the that's an I there. Just to go over the history of this reaction, Otto Diels in 1928 with his student Diels-Alder published this reaction. Now it's quite interesting because the Otto Diels actually worked for Emil Fischer, and Emil Fischer's one of my all-time favourite chemists because he did so much. You know, he did the Fischer-Endall synthesis and the Fischer projections, amongst loads of other things. And so it's a really good family of chemists. So they're all German chemists, and Emil Fischer, which I'll do tutorials on Fischer-Endall synthesis without a doubt, and I urge you to have a look at those tutorials. But so when Diels came up with this, and then Alder, his student, it just passed on and passed on. I think it's a great story, really, of how rich the organic chemistry was back in the early part of the 20th century. Anyway, just to carry on with the reaction mechanism, because I can digress, we'll just have a look at this transition state. The Diels-Alder reaction is called a pericyclic reaction. Pericyclic reaction. And all that means is that the transition state, so when it's reacting, the transition state is concerted. You get all the bonds being formed and broken at the same time, and that kind of locks the conformation of all the substituents around the diene and the dienophile. And that's really important because we do see a retention of stereochemistry. So if I draw the transition state for this simple species here, I'd have my 2 electrons here, like this separate molecule here. I'll just get a red pen, and we'd have something like the electrons from this diene attacking the dienophile. The dienophile gets full, so it pushes its excess electrons out, and it reacts with the other end of the diene to form this species here. This is all happening at once, so it doesn't happen and then it waits and then that happens. It all happens together, and you end up with a transition state where all the electrons are whizzing round. I'm just trying to get a red pen. It seems to be going orange. So all the electrons are moving together all at once. Now these are 6 electrons in this transition state. So that is an aromatic transition state. And like I say, it's all concerted, which means it all happens at once together. There's nothing happens first and then this happens. So it all happens together, and that returns the stereochemistry of anything that's stuck on here. It all gets locked into position. And your final product, as you know from the other tutorials, is the Diels-Alder adduct, which is the, in this case, cyclohexene with a double bond here. And if you draw the electron arrows, you have a look at this. If this double bond is losing electrons to form an underbond between this one and this one, if I label these carbons up as 1, 2, 3, 4, 5 and 6, then you'll see that these carbons are the same here, 4, 5 and 6. So the atoms are the points, as you should know by now, and the lines are the bonds, and these are the new bonds that have been formed here and here. The double bonds moved from here, and it goes between 2 and 3 now, and that's the Diels-Alder adduct. Okay, so that's really a basic recap of the previous tutorial. I'm just going to scroll down a bit now, and we're just going to have a look at the how the stereochemistry is retained and things like that. So I'll leave that transition state there. So the first thing to note when you're dealing with real systems and real compounds is you actually need to activate these. If you tried doing this reaction, you would need this particular reaction with just the ethene here. That would require so much energy to get that to go, because you've got electron-rich species there and electron-rich species there. They don't really want to, one's not attracted to the other at all, so there's no reason to react. So you have to increase that collision rate and really drive that reaction to completion. So what we do as chemists, we find alternatives to that. We mess around with the electron configuration of these reacting species, and to do that, the first and easiest thing to do is to add an electron withdrawing group. So in this case we've got the aldehyde here. So what does that do? Well, if we look at the resonance form of that, let's have a look. Let's move some electrons around that aldehyde. Move them around there. This electronegative, more electronegative than carbon, so it'll pull electrons to itself. And the resonance form for that, remember resonance forms are just different representations of the same molecule. There's no reaction going on, they're just moving the electrons around. Or minus, because it's got electrons there. We've now got a double bond across this, carbon and carbon. We've lost this double bond, we've lost this double bond. So let's draw that double bond in there. Now if we took electrons from this double bond, we need to sort the charge out. So the charge is resting on that carbon there, and we've still got that hydrogen, that's still there. Okay, so that's a resonance form. So you can actually now see, if you imagine this is like, I don't know, some liquid system, because that's all electrons are really. The fluid particles or waves, they will move around, and they will hover around, they'll hang around the one that's going to stabilise them the most, where they want to be. So if you imagine this is all free-flowing, wobbly jelly type of stuff, then you'll find there's not much electron density here, and there's a lot of electron density here. So that's all it's doing, it's just more attracted down here. The electrons tend to want to be around oxygen. But what we've done in doing this, in putting this electron withdrawing group on, is we've now made a site here which is quite nucleophilic. Sorry, electrophilic. So this electrophilic carbon here will be attractive to this nucleophile, which is the double bond of the diene. So now that will want to do that. Now this is still concerted. All we've done is we've made it more attractive to electrons, this part of the molecule. It's still, in doing this, will be drawing electron density from the other diene, which then makes this more attractive to electrons. And this carbon here hasn't changed. It doesn't actually feel any different. It's still got a double bond on that carbon, so that will act as a nucleophile now to attack here. So what we've done, we've set up the basic Diels-Alder system, but we've made it go with less energy. We've made it go with less energy because we've activated this double bond effectively. So that's the first thing to note with the Diels-Alder reaction. We have to have some activated species, otherwise we need to put in so much energy. So the product from this should be this molecule here. Okay, and I urge you just to go over the reaction mechanism. Look at this one, apply it to this. I've drawn these electron arrows off all this resonance form here. In fact, if I just take them out, and I can draw it back in. So let's, whoops, just get rid of them. Okay, so if I was to carry on with that reaction mechanism there, then all I need to do is get my brush back. Just do that, yeah. Okay, and that'll give me this species here. So just get rid of that dot. Right. So we've activated the double bond. That's the first thing. That's the first rule of Diels-Alder. If you want it to go to completion, you've got to have some kind of activation here. You could push more electrons into here, making this more electron rich, but then you're trying to get electrons to attack electron rich species. You're always better trying to take some electron density away so it reacts. Similarly, you could do it where the dienophile is electron rich, but again you find that this won't go that well because electrons are trying to attack electron rich species. The best way of doing it, like I say, is to take electron density away, and then it will react really, you know, room temperature or something like that. You might have to put some heat into it, but basically you won't have to have incredibly high pressures and incredibly high temperatures. So this is the first product. Now I'm going to label it up. The second thing to point out is the orientation. Now this is called the Alder-Stein rules, and it's quite simple to think about. If we label these up 1, 2, 3, 4, 5, 6 as before, we notice that goes like this, 5 and 6. So these, I'll just write this Alder Stein rules. Okay, Alder-Stein rules. And if you look at the resonance form for the dienophile, it's actually quite easy to understand why this happens, because the electrons from the diene will attack here first. Okay, so they're attacking that orientation. Unfortunately, this is not the best representation for that because we haven't got any substituent on here. But if I put a substituent on here, just as an example, I'll put it on in blue. You know, it's slightly different to the last one. Say we had some electron-rich species here, so methyl. That's a methyl CH3. Okay, and that's not a double bond. Okay, so we had this species, then we would end up with methyl. So the product would have a 1,6 substituent. Okay, substituents, and not 1,5, because if you imagine this flipping over, and let's just draw that down here. So the alternative to that would be all CH3 OH would be this, and that would give, oops, I'll delete that in a second. That would give this product. Oh, I keep writing CH3s and me's. Okay, I'll just delete that little bit. Oops, it's all gone wrong now. Okay, and that one. We'd have this product, I'll draw the double bond in, and not this one. So now it's substituted in the 1, 5 position. But we find that we actually just get this product here. Now these different types of products are very important. Sorry, that one's a bit misleading, isn't it? Looks like a double one. I'll move that over there. But okay, so you get it in the 1 and the 5 position. That's an alternative product. But we find that the actual product will be something like this. Okay, so it's attacking based on this kind of configuration. And if the only reason to understand it with this particular setup is if we draw the resonance forms for this as well. Okay, so it's a little bit of a digression here, but it's quite important to understand why we get certain products. We draw the resonance form for the diene with the activated methoxy group there. Then you can imagine the electrons of the methoxy group pushing into the diene like this, and that going like that, and then that one going like that. So I'll just draw one resonance form, and the product of that would be a double bond now for oxygen, CH3, so it still attacks that carbon. And then if we draw these carbons in, we've lost a double bond there, we're getting a double bond here. We've now got electron density here, okay, on that position there. Now if we just draw this resonance form here for the dienophile, plus on that carbon there, you can see that these are now orientating like that. So you wouldn't have it turned around for that to attack this. So the alternative, if I draw it upside down, would be it attacking here like this. So it's not going to attack that first and then try and form sorry, it's not going to attack carbon 2. It's not going to want to do that because this is more electron deficient. It's going to want to attack here, yeah, because that's electron deficient. So we're getting a match now between the positions of the electrons on the dienophile and on the diene. So that's a really good tip actually. Draw the resonance forms for your starting materials and you will be able to predict the orientation or the actual position, the chemoselectivity if you will, of the product. So this will not form because if you look at the way it attacks, it would have, for that to form, then that carbon would have to attack here, okay, and you can see that this one's more electron deficient. So I think I've answered that one now. Just going to scroll back up and see if I've missed anything on here. So that's the Alder-Stein rules, and that's the Alder-Stein rules can be explained using resonance forms, these resonance forms. Okay, so I think the only other thing to talk about with the Diels-Alder reaction now would be the Endall addition rule, and I'll just go over that a little bit because that really requires going into molecular orbital theory. Now molecular orbital theory is a really good way of explaining Diels-Alder reaction, but if you've never done molecular orbital theory, it's not very difficult actually, it's very pictorial. Then I recommend just have a look at the tutorial on Diels-Alder reaction, molecular orbital theory, just to understand it. And actually, for a lot of people, that's when it starts to make a lot of sense, and that'll explain the Woodward-Hoffman rules very well as well. So Diels-Alder reaction, the Endall addition rule, I will just go over it now briefly, like I say. And Diels-Alder, won the Nobel Prize in 1950, I think. So they won the Nobel Prize in 1950 for this reaction. And there's been a lot of spin-offs from this, actually, from understanding these pericyclic reactions and these thermally allowed reactions and things like that. So there's a lot of other Nobel Prizes come from similar kind of reactivities. So we'll just end now with the Endall selection rule, or Endall addition rule. Endall addition rule. Let's put addition like that, rule. Okay, and that's just to explain the orientation of the products. So if let's just get a different colour pen. If we look at diene here, and we'll call that R2, so it doesn't matter what it is, and we'll call this one, well, I'll make it an aldehyde just like it was before. Okay, now if it's orientated like that, or if I draw it in green, it could be orientated like that. Okay, put H on there, it's got H on there as well. Okay, now all I've done is I've flipped that over, but that's really important because we actually find in majority of products, actually, you get this one in this orientation, the Endall position. So this is the Endall, and this is the XR. So XR just meaning outside, really. So if you look at the transition state, see if I can do this. Let me just, don't know how good this is going to be. I'll copy that, and what I'll try and do, if we look at this one, I'll copy that as well. If I try and just put that over here as it's about to react, it will orientate itself on top so that these double bonds here are lining up with these ends here. So imagine that molecule's coming over the top there. It's not very easy to see because I've got that little, I'll just drop it in there like that, actually. So we got, if I group that, I might be able to get that out, actually. So we've got it in that position there where it's just on top. Now it looks very messy, but actually this is what's going on in real life in the reaction. This will position itself. It's got to position itself first. The energy's got to be right. Then it's got to react. So it's a lot of things got to happen before the Diels-Alder reaction takes place. Now you'd think that would be based on steric hindrance. You've got protons here and you've got this one over here. You'd think that actually be the more favoured product because this big group here is sticking out into nowhere, so it's not going to hinder the reaction. But if I just take a copy of this one, copy. Oops, I didn't get that hydrogen, did I? Let me just do that again. Get rid of that one. Okay, if we look at this one now, as that orientates itself, in fact, what I'll do, I'll just colour that red. Orange or red. If you look at this one now, as this one is over the top, it looks like there's a lot of steric hindrance. Imagine this aldehyde stuck above it and it's just about to react with that. You'd think that would be more hindered. But if you look at the molecular orbitals of these things, just get out of that. If you look at the molecular orbitals, these are double bonds and these are double bonds. And all these double bonds here, like these other double bonds being around them. So it actually favours the Endall transition state because, so the Endall transition state, let's see if I can draw it. Let me just grab that again. So it's actually the double bonds that are making this work because these double bonds in the carbonyl can overlap with these ones here, and that actually stabilizes and lowers the activation energy for the reaction. So that's actually more stable than the alternative of these double bonds being on the outside. So that's not easy to see in this tutorial because we're just drawing double bonds, but I urge you to have a look at the molecular orbital tutorial on this, and you'll see that these p orbitals from that carbon and that oxygen sit really nicely. It's uncanny really how they interact with these other double bonds. So the Endall addition rule, just for this tutorial, is the fact that the Endall product, the one with this group overlapping the diene, is the more favoured. Just for this tutorial. There are examples where the steric hindrance is just too bad and it will collapse, but in a general rule, the Endall transition state is more favoured. So what's the product from that? I've not drawn that yet, have I? So let's just get rid of these. So what is the product after all that chit chat? Put that there. The product from that would be, let's get rid of that actually. If I react this now, let's get myself a nice red pen. So remember, this is going to react like this, going to attack there. That's going to go there to form a double bond across there. That's going to go there like that. And the product will be from that a 6-membered ring. Let's remember, this Diels-Alder reaction forms 6-membered rings. The double bond goes in there. If you ever see a molecule with cyclohexene ringing like that, you've got to think Diels-Alder. That's probably how it's been made. Now we know where that group is, R2 there. It's stuck there on that carbon, and I'll label these up in a second. Now if that was sticking up, which it will be, which is another thing I've not really spoke about, we've got to now think, if that group there, that's the whole point of this bit actually, if that group there is going in that position, and that's going in that position too as it goes over the top, and that hydrogen there is going in that position, that's going in that position there, then this one should be the same position relative to that. So if I do that as up, whoops, that's terrible. If I do that as up, and we do that with a wedge like that, I'll just colour that in a little bit, then that hydrogen that was also on there, oops, must have gone down. This hydrogen here must have gone down. If this here is facing this way, then that also must be up, and that hydrogen there must be down. So there's your carbonyl. Okay. Now that's not very clear to see, and you really have to start drawing these 3D models, and I'll try and put a 3D model up somewhere for this as well, so you can actually see how these interact, and as this bond forms you get the orientation. You could also use a Newman projection or something like that. I don't know whether you've done Newman projections. That's a really good way of drawing it. Or, as I'm about to attempt now, you can try and draw the transition state. So you've got a 6-membered ring. You draw it like that. And remember that you're going to have a double bond forming around here. Then that R group there will tend to push downwards like that. And that hydrogen will go there like that. And then if I draw the other bit approaching, as the aldehyde approaches with the double bond, then you'll have, it's not easy to draw with this pen actually, you'll have the aldehyde there like that, and the hydrogen going back there like that, and then you've got 2 hydrogens there, and then it will be trying to form a bond across there like that, and that's not very good, I know, but basically I'm trying to try and turn this into a tetrahedral structure, this carbon, because that's what it's going to become. It's going to become tetrahedral here, and this is going from a flat sp2 structure, which is basically that shape, flat, to tetrahedral structure like that. Okay, so flat to that. and in doing that it has to bend and push these groups out of the way. And if it's got this orientation where it's overlapping with the orbitals, then it can quite easily form the bond like that. So I'll put a 3D structure up for this, because it's not that easy to draw on here, and it's not easy to for you guys to actually understand this. So a 3D model is perfect, and I'll put that up with this as well to explain what's going on here to retain this stereochemistry and stuff like that. But basically the most important thing is the Endall addition rule is because of these overlapping p orbitals, and that will lead on to molecular orbital theory. So I'll just put that down there. Molecular orbital theory. Okay, and that will explain all this in a lot more detail than a two-dimensional drawing of these compounds. And that is basically the Diels-Alder reaction. The Diels-Alder reaction.